Radical and exponential forms. So up until now, we've been talking about monomials, and we've been multiplying and dividing with monomials, really thinking about powers, thinking about the bases, thinking about the exponents. So now we're going to switch gears a little bit and talk about radicals and exponential form. So we're thinking about taking that monomial and thinking about really focusing more on the base and what we're doing with the base. So for any non-negative number, b to the 1/2 is equal to the square root of b. So this is called our radical symbol here, this what we've referred to as a square root up until now, but it's really a radical symbol. And what's inside that, what's underneath our radical symbol, is called the radicand. So we're going to work a little bit here with thinking about our roots. So when I think about the root of something, I'm thinking about, well, this is a power, but where did that come from? Where did that start? Where did that power actually come from? If you think about a tree, the tree root, where did it start? So we're going to write each of these in radical form. So again, this is our radical form here, where I use my radical symbol. And then this is our exponential form, where again, we think of it as writing it as a base with a power, with an exponent on it. So exponential form, radical form. So we're going to write each of these expressions in radical form. So you notice that here I have a fraction as my exponent, which is probably the first time you've seen that. I've got a radical here, and you'll notice that this is a square root. We're thinking about squaring it to the second power. So this 2 here is really coming from the fact that we're talking about a square root to the second power. So a to the 1/2 is really the same thing as the square root of a. So this is, if I find the square root of a, that's a to the 1/2. Same thing. They represent the same number. They represent the same. They represent the same number, but they're just written in 2 different forms. So this is our exponential form. This is our radical form. So again, I can take my 7w. I've got 7w to the 1/2 power. If I write that in radical form, I'm going to put, this is going to be my radicand inside my radical symbol. So here's my radical symbol, and my 7w is on the inside. So again, this is a square root. I've got to the 1/2. Okay, so I'm going to the second power there as far as my root goes. Write each expression in exponential form. So now we're going to go from that radical form to an exponential form. So I've got the square root of 22, so I'm going to flip that. This radicand becomes my base, so my base of 22, and my exponent is going to be 1/2. So again, that 1/2, that 2, thinking about that it came from a square root. And my last one here, I've got 3 to the square root times the square root of x. Remember that this is 3 times the square root of x here. So this is a 2, when 2 are together like that, we always know that that means multiplication. So notice that I end up with 3 times x to the 1/2 power. Notice that these two things are different. Notice that here, that the whole base is 7w because it's in parentheses. So the exponent is 1/2, the base is 7w, so the base is going inside the radical symbol. The base is my radicand. Here, the only thing that's in the radical symbol is the x. So that is the only thing that's my base here. So it's x to the 1/2 power. The 3 is really, again, just being multiplied by that. Please remember that when we talk about these with our exponents here, our exponential form, that exponent is only working on its base. It's not working on the 3. All right, let's continue with our radical form here. For any real numbers a and b, and any positive integer n, if a to the nth power is equal to b, then a is the nth root of b. So here we talked about, this is basically the second root to the second power. To the second root, we're squaring it. It's got a root of 2. That's our 1/2 there. So when we talk about the nth root, here we'd be talking about the second root, the third root, the fourth root, the fifth root. We can use any number as far as we go there. So if we think about this, we're kind of undoing an exponent. That's really what we're doing here. So the nth root of a to the nth power would just be a. They're basically canceling each other out is what's happening here. Here I'm using this as an exponent. I'm kind of doing it to a power, that base to a certain power, multiplying again and again and again. Here I'm going backwards and saying, well, where did you start from? If you multiplied this many times, where'd you start from? Well, I started from a. Okay, so that coming back to that. So these two are basically opposite operations of each other. Finding the root and finding an exponent, those are basically opposite operations of each other. So if I want to simplify these, I have the cube root, or the third root, we can call this the cube root, we're used to calling that. The cube root of 64, well, this is the cube root of 64 is 4 times 4 times 4. So that's 3 the cube root of 4 cubed, which is then 64. So I can rewrite that 64 as 4 cubed so that they kind of cancel each other out, which just gives me that 4 as my simplified version of that. And last one here, we've got the fourth root of 10,000. So again, 10,000 is 10 times 10 times 10 times 10, which is 10 to the fourth power. So that fourth root and that fourth power cancel each other out, and I've just ended up with 10 here. So again, these are kind of opposite operations there, finding the root and finding the power. All right, let's keep going with our roots here. For any positive real number b and any integer r which is greater than 1, so again, we're not getting into the negatives, we're not getting into the zeros at this point, b to the 1 over r power is the r root of b. So you'll notice that what the denominator is here is basically whatever the root is that we're talking about, which worked with that square root. We talked about the square root. It has an exponent of 1/2. It's a square root, the second power. That power was in the denominator. So the denominator here is basically what the root is, the denominator of that fraction. So we're going to simplify each of these, and sometimes it's easier to simplify them if I write them in that radical form. So 64 to the 1/3 power, well, that really is the cube root of 64. Again, that denominator is our root. So cube root of 64, well, 64 is 4 times 4 times 4. That's 4 to the 3rd power. Again, that cube root and that third and that exponent of 3 cancel each other out, so we end up with a simplified version of 4 there. So 64 to the 1/3 power is 4. 81 to the 1/4 power. So again, this is basically our root here, the 4. So I put the 4 on the outside of my radical symbol. I'm looking for the fourth root of 81. So I'm looking for what can I multiply by itself 4 times to get 81. Well, that would be a 3, because that's 3 times 3 times 3 times 3. So I have the fourth root of 81 would be 3. As we get comfortable with these, you do not need to write this out this way. I'm writing it out this way just so you can kind of see why that is working the way that it is. All right, last piece of this. For any positive real number b and integers e and r has to be greater than 1, b to the e over r power, equals the r root of b to the e power. So think of this as your exponent, think of this as your root. So again, we had our root there as our denominator. So think of your denominator as your root, think of your numerator as your exponent. So the exponent goes on the base, onto the base on the inside there, and our root goes outside the radical symbol. So b to the e over r power becomes the r root of b to the e power. Another way we could write it is we could put the r root of b inside parentheses and all to the e power. So here I would be thinking about finding the power first and then finding the root. Here I would be thinking about finding the root first and then finding the exponent. And you might see a problem and decide one way makes more sense than the other depending on what numbers you're working with, as we'll see when we look at these next two examples. So here we're going to simplify 27 to the 2/3 power. So again, I've got my exponent of my root basically. So I'm going to put my cubed outside my radical symbol and my second power with the 27 as its base. So I have the cube root of 27 squared. So here I'm going to square the 27, and I get 729. And now I'm going to find the cube root of that, and I realize that 729 is 9 cubed. So we're looking at the cube root of, did I miss something there? This is just a 9 here. What crazy numbers are we putting here? This is just a 9. So our final answer is 9, because this is the cube root of 9 cubed. So that cube root and that cubed on the inside cancel each other out. They're opposite operations. And I end up with a 9 here, not the cube root of 9. Just plain old 9 here. So 27 to the 2/3 power is 9. And last one, 256 to the 5/4 power. So again, my exponent over my root. So my root goes on the outside of my radical symbol. My power came onto the outside here. Now I chose to put the parentheses around the radical because I looked at this and said, oh my goodness, do I want to do 256 to the 5th power? That's going to be really huge. So let's see if I can find a fourth root of 256 first. If I can find that first, then great. If I can't find that first, then we'll work around it. So I'm looking for the 4th power of 256. Luckily, 256 has a power of 4 as one of its products. So I found out that that was 4. So 4 to the 4th power is 256. So this simplifies to 4. And now I have to do 4 to the 5th power, which is not so cumbersome to do. I end up with 1024. So manipulating around, working from our exponential form to our radical form, and using that to help us simplify exponential expressions.